Okay, this is Chapter 4, Reactions and Reaction Stoichiometry, and this is Lesson 1. In tonight's lesson, we're going to talk about water as a solvent, strong and weak electrolytes, solution concentration, and how to make a solution. As you can see, there are quite a few objectives, so how we're going to break this down is water as a solvent up to how to make a solution will be Lesson 1. Types of reactions, introduction, precipitation, precipitation reaction stoichiometry, acid-base reactions, and acid-base stoichiometry. That is going to all be Lesson 2. And then the third lesson we will finish up with oxidation, reduction reactions, redox stoichiometry, and just reaction predictions overall. So there will be 3 lessons in this unit. Some of what we're going to go through today is going to be a review from Regents Chem, and some of it will be a little bit new. So let's just go through definitions of molecules and ionic compounds. As you recall from Regents Chem, a polar molecule has, as I used to say, pull, which means that there is an unequal charge distribution. We also say that this molecule is asymmetrical. We may also say that it has a dipole. And what that means is you have a slightly positive end and a slightly negative end. So an example of this, something that you're very well familiar with would be H2O. Now, what I did here was, we know that oxygen has 6 valence electrons and each hydrogen has 1. So remember, each bond line contains 2 electrons. So this bond line contains an electron from H and 1 from O, and the same here with this H. So if each H has 1, that's a total of 2, and oxygen has a 6 valence electrons, that's a total of 8. So we've got 2, 4, 6, 8. And then we look at electronegativity to determine what's going on with the charge distribution. So we know that oxygen has a higher electronegativity than hydrogen because it's closer to fluorine. So this side is going to be slightly negative and this side will be slightly positive. And this little symbol is delta. So we're showing that this side of the molecule is slightly negative and this side slightly positive. In a nonpolar molecule, there is no pull, meaning that there is an equal charge distribution. And we want to make sure that we put down that it is symmetrical. And I would also like to include Brinkelhoff here, because all Brinkelhoff molecules are nonpolar. Br2, H2, F2. Ionic compounds. Ionic compounds are usually between a metal and nonmetal, whereas our polar and nonpolar molecules are nonmetals. And due to the transfer of electrons, a positive and negative ions are formed. And the positive and negative ions are attracted to one another because one atom gave up an electron, one atom gained an electron. These formed positive and negative ions. The electrostatic charges attract one another and they form a bond. They form a crystal lattice, and that's the picture, the three-dimensional model in the classroom with the sodium chloride, the green and silver balls there. Remind me to show that to you. With alternating positive and negative charges. And I'm sure there's a good picture in your book too. Okay, so that's a review of that. Now, one of the reasons that water is used as a good solvent is because it is asymmetrical, and when we put another substance with water, something happens and it dissolves. So let's talk about what happens. What you see here is how water surrounds the positive and negative ions. So what happens is that the alternating positive and negative ions in the ionic compound attracts the water molecules. Now remember, the water molecules have a positive and negative end. So the H2O molecules pull the ions away from the central crystal. So say this part down here in the bottom is the central crystal. They surround and pull away due to the attractive forces, and they pull them away from the main crystal. And then it dissolves in the water. Now, a polar substance dissolves in water as well. And what happens here is that the water molecule surrounds only a portion of the molecule that has a charge. So the example that I can think of here is ethanol. So let's take a look at ethanol. Ethanol is a 2-carbon alcohol. Okay, so remember that all of these little lines are H. So the chemical formula for ethanol is C2H5OH. Okay, so there's my ethanol. Now, most of the molecule of the ethanol molecule is nonpolar. Okay, there's equal and opposite here, and equal and opposite here. What happens is, up here, where this OH is, here's where there's a polar bond. Okay? This right here is the polar bond between the O and the H. So the O is slightly negative, and the H is slightly positive. When I take alcohol and I put it in water, what happens is, here comes the water molecule, and I'm drawing it this way purposely. The H side is slightly positive, the O side is slightly negative. We get this attractive force between the O and the H, and this pulls this away, apart, and then the alcohol can dissolve. So the main point to remember here is polar dissolves polar because of the fact that most of the molecule is actually nonpolar, and the water works on the polar end of the molecule. Okay, let's talk about a nonpolar substance with a nonpolar substance. So nonpolar means that there's no charge. Okay, because there's equal charge distribution. I should say no net charge. But the electrons are always moving. And because of that, we get temporary areas of charge. So what happens is, say you have a substance and the electrons are constantly moving, constantly moving, constantly moving. Well, as the electrons move, and this is in an instant, one end of the molecule can become slightly negative, one end can become slightly positive. And then if that's near another molecule that's electrons are moving fast, then there can be an extremely weak electrostatic force between this positive and negative. And this is extremely weak force. So this is showing you an example of CCl4, which is nonpolar by symmetry. Okay, because it looks like this. So we have that asymmetrical. Remember, the bond between the C and the Cl is going to be polar, because the Cl has a higher electronegativity than the C. However, the overall molecule is nonpolar because it's an equal and opposite pole. C6H14 is hexane, and hexane is a ring so it kind of looks like that, but that's also and these are your C's. We'll talk about that later on. This is also nonpolar. So this is why you have distinct layers here, because you have nonpolar, polar, and nonpolar, and they will not dissolve in one another. Nonpolar can only dissolve nonpolar. So if I got rid of the water and I put the CCl4 and the hexane together, then they would mix. Alright, remember strong and weak electrolytes. An electrolyte is something that has the ability to conduct an electric current. And normally when we're talking about an electrolyte, we're talking about an acid, base, or salt. So a strong electrolyte is something that completely dissociates in water. And a strong electrolyte would be your salts and your big six that you had to memorize, your big six strong acids. So an example of this would be NaCl, aqueous, so I've put the NaCl solid in water and it dissociates into Na plus and Cl minus. And that's 100% dissociation. A weak electrolyte only partially dissociates. And an example of this would be acetic acid, which is vinegar, which is very weak. So we've got HC2H3O2 and we have H plus aqueous and C2H3O2 minus aqueous. And this is at only approximately 1%. So what that means is that the acetic acid pretty much stays intact. It does not dissociate. So this would be 99% in this form and only 1% in that form. And non-electrolytes, as you might have gathered, are covalent compounds. So we mean made up of non-metals, and there is no dissociation. So if I have sugar, C6H12O6, aqueous, it's C6H12O6 aqueous. It still dissolves because it is polar. But it does not dissociate. I will do a demonstration of this in class. Oh, here's your demonstration. So I did this in Regents Chem, but I will do it again in this class because some of you haven't had Chem in 2 years. But we're basically going to have 3 different solutions, and we are going to see what happens when we put a probe with an electric current in salt water, sugar water, vinegar, which is the acetic acid, and then I'm also going to show you with a strong acid so that you can see that. So I'm going to show you 4 different little mini demos, and we'll talk about this. Now what this is showing you, hypothetically, is that there's 2 probes that stick into the solution. One's a positive end and one's a negative end. And when we connect it to a battery, we complete the circuit. So essentially, if I put salt in water, remember what happens. The water surrounds the sodium chloride crystals and pulls them apart. And so you have Na ions and Cl ions floating freely in solution. And the Na positive charges are attracted to the negative electrode, and the Cl negative charges are attracted to the positive electrode. Okay, let's move on to solution concentrations. There are many ways to measure solution concentrations. In chemistry, the primary way is molarity, which you're very familiar with already. Molarity is equal to moles of solute over liters of solution. So if I say that I have a 6 molar HCl solution, that basically means that I have 6 moles of HCl per 1 liter of solution. Some other helpful equations that you might see: MV is millimoles. So when we're using milliliters, and sometimes it's also easier to do calculations. So basically how this works is if I have 6 moles per 1 liter and I'm changing to milliliters, my liters cancel and I am left with 90 millimoles, not millimeters, millimoles. So let's do some calculations. Calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous HCl into 26.8 milliliters. So they want us to calculate molarity, and molarity is equal to moles over liters. So we're starting with 1.56 grams of HCl. So the first thing that we want to do is change this to moles. So we know that 1 mole is equal to 36.5 grams of HCl. So my grams of HCl cancel. I have 26.8 milliliters. Now I could have done this as one dimensional analysis. I'm going to show you in 2 steps, and then you can figure out if you wanted to do it in 1. So this is going to give me 4.27 times 10 to the minus 2 moles of HCl. Hopefully you're doing your math as well and checking mine. Occasionally I do make a mistake, so let me know. And we did this in 26.8 milliliters, and we need this in liters. So I think we all know 26.8 milliliters is equivalent to 0.0268 liters. Okay, milliliters to liters, we move the decimal 3 places to the left or divide by 1,000. So now I've got moles divided by liters, and I'm going to get 1.59 molar. How I probably would have liked you to do this is 1.56 grams of HCl per 26.8 milliliters. So we said that 1 mole is 36.5 grams of HCl. These cancel, and I know that 1,000 milliliters is 1 liter, and milliliters cancel. Now I just want to check the math on this to make sure that we get the same thing. We get the same answer, 1.59 molar. So it's however you feel comfortable doing it. Let's do one more. Typical blood serum is about 0.14 molar NaCl. What volume of blood contains 1 milligram of NaCl? So, as soon as you see molarity, light should start flashing, and molarity is used as a conversion factor. So they gave us molarity in the problem. This is not what you start with. What this means is that you have 0.14 moles per 1 liter. We're going to start with the milligram of NaCl because we want to know what volume of blood. We're going to wind up using the concentration of salt in the blood as a conversion factor. So 1.00 milligrams of NaCl. And the first thing that we need to do is get this into grams. So 1,000 milligrams is equal to 1 gram. That's that. Now we need to get this into moles because I have this conversion factor over here on the right that has moles in it. So we know 1 mole of NaCl has a mass of 23 for the Na plus 35.5 is 58.5 grams of NaCl. And this was NaCl. So 1,000 grams of NaCl is equal to 1 gram milligrams of NaCl. So sorry, these cancel. Grams cancels. I have moles. I'm not done yet. We know that 0.14 moles is equivalent to 1 liter. Moles of Na cancel. Moles of NaCl cancel. Because this was 0.14 molar NaCl over here. So now I've got 1 times 1 times 1 divided by 1,000 divided by 58.5 divided by 0.14. And I'm going to get 0.03 0.0000122 liters, or better expressed as 1.22 times 10 to the negative 4 liters of NaCl. We're almost done. How do we make a solution? Well, you're going to be making solutions soon in lab, so it's important that we know this. So first of all, there are two ways. We got with a solid and with a liquid. So essentially, you're putting a solid into some type of solvent, or you're putting a liquid into a solvent. So let's talk about the first one. This is a solid. The procedure part is easy. You take your solid, and this is what's called a volumetric flask, which means they come in different sizes, 50, 100, 250, 1,000 milliliters. So this is the predetermined mark. So you put your solid in, whatever you weighed it out that you wanted it to be. You put some distilled water in, you swirl, and then once all the solute is dissolved in the solvent, then you continue to fill it up with distilled water, and you make sure that the bottom of the meniscus is on this line. So what are some steps that we can do here? You're first going to determine what you want to make. And then the second thing you're going to do, let me give you an example here. So an example might be 500 mils of 0.1 molar barium nitrate. Okay. Second step. You want to determine the grams you need to weigh out. So in this case, we can use molarity equals moles over liters, and you can use moles equals given mass over GFM. But I'm going to just do what I need to do. So I want to make 500 milliliters. So what do I know? I know that 1,000 milliliters is 1 liter. So milliliters cancel. And I know that molarity is moles per 1 liter. So in this case, this molarity, this 0.1, remember I told you was used as a conversion factor, is equivalent to 0.1 moles per 1 liter. So 1 liter, 0.1 moles. and this is of the barium nitrate. Liters cancel. Well, I know that 1 mole of barium nitrate has a GFM of 261.3.